So kinetics studies the rate of reaction and the factors that affect those rates. It's pretty much how fast can a product be formed. The energy barrier of a reaction, shown as delta G with this little plus plus, is called the free energy of activation. Delta G plus plus is free energy of transition state minus free energy of reactants. So transition state minus reactants. High delta G plus plus is slow reaction. Plus plus is not the right word to use. We can just say high delta G plus equals slow reaction. So this right here is a slow reaction, while this right here is a fast reaction, right? Low delta G equals fast reaction. When we're calculating delta G plus, it's going to be delta H plus minus T times delta S plus. It's pretty much the same as a regular delta G, but now we just say of transition state. So delta H plus is the enthalpy transition state minus enthalpy reactants. Delta S is the entropy transition state minus entropy reactants. So that right now we take into consideration transition state and reactants. Right, because in this case we're going to be having like the multi-step reactions, right? It's not just reagents minus reactants. There's going to be that transition state right in there, right? Which is that right in the middle, right? So thermodynamic stability, delta G zero. Negative delta G zero, the thermodynamically stable products, right? Products are favored. Products favored. Then we have a positive delta G and it's thermodynamically unstable. In kinetic stability, a large delta G means that the reagent is kinetically stable because there is a slow reaction. Small delta G means that the reagent is kinetically unstable because there is a fast reaction, right? So this right here is going to be unstable, while this right here is stable because it's slow. Unstable because it's fast. Okay, so right here, negative delta G is exergonic, right? Thermodynamically stable. Products are more stable than the reactants. A small delta G plus means there's a fast reaction and it is unstable, and a large delta G plus means it's slow reaction and it is stable. So right here, right, we have an example of exergonic, and there's one with a small delta G plus and one with a large delta G plus. So we need to add heat to make it more forward at a reasonable rate. And then down here we have a positive delta G plus, which is entergonic, which is thermodynamically stable. Products are less stable than the reactants, and again we have both examples. Small delta G, fast and unstable. Large delta G, slow and stable. And again we have to add heat to make it move forward at a reasonable rate because it is so slow. So rate of reactions is going to be number of collisions per unit time multiplied by fraction with sufficient energy multiplied by the fraction of proper orientation. So how do we increase reaction rate, right? We can increase the concentration of our reactants, which increases the number of collisions. We can increase the temperature, which increases kinetic energy, and the result of that are a greater number of collisions with a sufficient amount of energy. So adding a catalyst as well changes pathway of a reaction to have a smaller delta G plus. So now we have rate equations, and there's like a bunch of stuff to get through. I'd say just put on your note card. So A to B, rate equals K times A. K is how easy it is to reach the transition state. Okay, it is independent of concentration. Small k means high energy barrier, slow reaction rate. Large K means low energy barrier, fast reaction rate. Okay, it's a constant. Rate of reaction is how much product is produced per unit time. It depends on rate constant and concentration of reagents, and it is affected by temperature as well. So K tells whether it's faster or slower, and it is independent of concentration. Arrhenius equation and the rate constant. So K is temperature dependent, right? K is A times e to the power of negative EA divided by RT. K is going to be the rate constant, right? And so that's why we set up here that, where did we say this? It depends on rate constant, and it is affected by temperature as well. Affected by temperature as well because the rate constant down here is affected by temperature, right? So A is going to be the frequency factor, collisions with proper orientation. this whole thing is going to be collisions which occur with the minimum energy EA for the reaction to occur. Negative EA is the experimental energy of activation, R is the gas constant, capital R is the gas constant, T is temperature in Kelvin, RT to speed up reactions. If you increase temperature by 10 degrees, it doubles the rate constant and the rate of reaction. So rate constant to equilibrium constant. At equilibrium, A is going to be like that, right? Equilibrium B. Forward rate equals reverse rate. So Ka equals K minus 1B. K equals is represented like that.